Welcome to the 30th lecture of the course Discrete-time Markov chains and Poisson processes. So, just recall that in the previous lecture we have talked about strong Markov property. So, strong Markov property basically tells us that, well, if I know that at some stopping time the state is I, then Markov chain actually starts afresh from there. Only thing is that the initial distribution is delta I and the transition probability matrix is same as the previous transition probability matrix, and not only that, the two part of the Markov chain becomes independent. Okay? So, we have seen this property in the last lecture, and then we have seen how this can be used to solve or find out probability of some random variables concerning the Markov chain. Okay. Today we are going to see what is called classification of states. That basically mean that we will going to define two kind of states, and each states will be either one or the other kind. So, it is kind of a exclusive, that in the sense that exhaustive and exclusive in the sense that one state I will be either transient or recurrent. These two state we are going to see, one is transient state, another is recurrent state. So, let us start with. So, the idea behind this transient or recurrent states are as follows, that suppose I have a state I and I start from the state I, and the question is that whether I will come back to the same state, the ith state again in a finite time or not. If I come back in finite time, we call that corresponding state is a recurrent state, and if we do not come back to that state in a finite time, or rather there is a possibility that we will not come back to the state in a finite time, then that particular state is called transient state. Okay? So, if I come back in finite time with for sure, then it is called a recurrent state. If I do not come back for sure, then basically it is called a transient state. So, the thing is something similar to think about your hometown. Okay? So, you may be, because of your college or because of your job, you may be outside of your hometown, but in finite time you actually come back to hometown to see your relatives, your parents, maybe your family, other family members, and all members there. Okay? So, it is some kind of that, but that is basically the hometown is something close to our recurrent state, and then suppose we have a third city, maybe we went there for some visit, maybe I went to Darjeeling to visit it, or maybe I went to Guwahati to visit it. I like the hill station, so I went to those places, but I may not come back again to that place. I may come back, I may not go back to those places for sure. Okay? So, this kind of state, this kind of places which is not my hometown may work as a example or something close to transient state. Now, this is the intuition. Now come to the mathematical definition of this thing. So, to define this thing, we have to start with something which is called the first passage time. So, what is first passage time? The first passage time for a state I for a Markov chain Xn is defined by Ti, and Ti is a random variable, and it is defined by this particular expression. What is this? This is nothing but Ti is the infimum of the set. I am taking the collection of all possible n such that n is greater than equals to 1, such that xn is 1, xn is I. Okay? I am taking the collection of all n greater than equals to 1 such that xn is I. So, this Ti is called the first passage time. So, let us try to understand what this means. See, we have seen something very similar to this, which we call the heating time, and we define the heating time Ti, or in general Ta, as infimum of the set, n greater than equals to 0 such that xn belongs to A, or when A is singleton. If I take A is singleton I, we define Ti which is equals to infimum such that n is greater than equals to 0, such that xn belongs to A, and here A is a singleton set. So, I can write xn equals to I. So, the only change between heating time and that first passage time is that in this case I have taken n is greater than equals to 0, and in this case I have taken n is greater than equals to 1. And the difference that makes is that if I start from I, then Ti is 0, but if I start from I, that T underscore I is not equals to 0, the reason being that 0 is not in this set, and so infimum cannot be 0, n is greater than equals to 1, so infimum cannot be 0, okay, infimum cannot be 0. So, this is the main difference. Now, let us try to understand this in word. So, what happens is that a Markov chain actually start from 0, and maybe that it just proceed like that, okay, it just proceed like this, and maybe this is the state I, this is the state I. Now, what happens, it start from somewhere, and then maybe this is the time 1, time 2, time 3, so on so forth, maybe this is the time 5. At the time 5, it actually come to the state I for first time. And so, this set, if you see, 5 will be there in this set, and then maybe some more than 5 values will be there, n greater than 5, some n greater than 5 values will be there, but when I am talking about the infimum of this set, that turns out to be 5. Okay. When I talk about the infimum of this set, that turns out to be 5, because 5 is the minimum value in this particular set, along with some values, along with some n is there which are greater than 5, which are basically these points, when we visit the state I, because xn equals to I. Okay. So, that means the difference between these two basically can be written in this way, that Ti is basically the first time the chain visits state I after time 0 excluded. Okay, 0 excluded, but in case of T upper I, this is basically the same thing, the first time the chain, the Markov chain enters state I after 0, here 0 included. Okay. So, this is the difference between the heating time and the first passage time. In case of heating time, 0 is included. So, if I start from I, in 0 time I will be in I, so heating time will be 0, but in case of the first passage time, it is basically once I see I, then after how many times I will again come back to I, that is the important. Okay. Once I see I, then after how many time I come back to I once again, that is the important in case of the first passage time. So, the 0 is not included, that is why the change is that both of them is after 0, but in one case the 0 is included, in the other case the 0 is excluded. Okay. So, this is basically the first passage time. And now, using the first passage time, now we are going to define what is called recurrent and what is called transient. The transient state is defined as follows. A state I is called transient if Pi Ti less than infinity is equals to 1. Recall that this Ti, just let me draw the picture. I start here from I, the state is I, and the time is 0, at the time 0 the state is I, then in the finite time if Ti is basically nothing but again I come back to I, from I again I come back to I, and in between there is no I, okay. So, that means that I start from I and I come back to I at the time Ti, and that recurrent, the state I is recurrent if I come back in finite time. Starting from I, if I come back for sure in finite time, we say that the state is recurrent. So, pi ti less than infinity is equals to 1. That basically mean that starting from I come back to I in a finite time for sure. Okay, starting from I come back to I in a finite time for sure. Okay, and on the other hand, the transient state means that a state I is called transient if this probability is less than 1. If this probability is strictly less than 1, that means that there is a positive probability. That means that pi ti equals to infinity is greater than 0, and that says that there is a positive probability that starting from I will not come back to I again. Okay, there is a positive probability that starting from I will not come back to I I will not come back to I. Okay, so there is a chance that I will not come back to I starting from I. If such thing happens for a state I, we call that corresponding state as transient state. If for sure we come back, we call such kind of states as the recurrent state. Okay, so now let us see this remark. The remark is important in the sense that that gives us some intuition about recurrent state. Such kind of statement we will see later about the transient state. Let us first talk about the recurrent state. So it says that I is recurrent, the state I is recurrent if and only if this thing happens. What this mean? This basically mean that if I start from I, then xn equals to I for infinitely many n, this probability is 1. Starting conditioning on that, on the fact that I am starting from I will come back to I for infinitely many n, that probability of that event to happen is 1. So for sure I will come back to I again and again. So this basically mean that these infinitely many n I xn equals to 0, that basically mean that the state I is visited again and again. The state I is visited again and again. Okay, so this statement, this remark basically tells us that if I is a transient state, then I will visit the chain starting from I, the chain will visit the I state I again and again, again and again, again and again. Okay, so it will be visited for infinitely many times. So that xn equals to I for infinitely many n, that will going to happen with probability 1 if I am starting, or the chain is started from state I. Okay, so how we can prove that? The proof is simple using the strong Markov property. So what happens? Suppose at the time 0 the state is I, because I am trying to find out the probability under the condition that x naught equals to I. Okay, so now after some time it will come back to state I, it will come back to state I for the first time, which is the time ti according to our definition. Now let us take t equals to this, and this t is basically, now we have actually talked about this is a stopping time. We can show this is a stopping time. There is no difficulty in showing, and the proof is just the same as showing that heating time is a stopping time. Okay, the first passage time is a stopping time, showing this one is almost similar to that of showing heating time is a stopping time. So just check that whether you can able to show that or not. So this is a stopping time. Now in the strong Markov property, I take this ti as the time with respect to which I am conditioning, because I know at ti the state is also I. So now if I condition on two fact, one is ti is less than infinity and x ti is equals to I. That is true, that is always true. That is always true because this is the first passage time. So that is always true. At the time point ti, the state is I, there is no question about that, but I am conditioning on ti is less than infinity. So what happens? The strong Markov property says that this part actually again start from afresh. Okay, this part is a Markov chain, a fresh Markov chain which is basically starting from I. So it is a fresh Markov chain, but the delta, it is the initial distribution is delta I, it is starting from I. Okay, so and this part are independent, these two parts are independent. That is the strong Markov property tells us. Now use this thing. If I use this thing, then the Markov chain is starting from here afresh and it has no effect of the previous thing. So if I rescale this time to 0, then after some time again the ith state will be visited, So that means that I come back to I again starting from here the state is I will again come back to the state I after some time, again starting from here I will again come back to the state I after some time. Okay, so the state I will come back again and again using the strong Markov property with probability 1. Okay, and that actually shows that one part, that if I is recurrent, then it shows that this condition holds true. Okay, if I is recurrent, then this condition holds true. And the other side is trivial, that if this quantity holds true, that means the starting from I, the state I is visited again and again. That basically means that starting from I, at least once I am coming back to I for sure, in infinite time for sure, and that is exactly the definition of the recurrent state. Okay, so let us just go through this argument once again. Let us remove this part and let us write this thing very clearly. That so basically I start with the fact that suppose I is recurrent. Okay, now I use the strong Markov property. So what the strong Markov property tells, that well, if I start from here, basically I am talking about I am starting from I at the time 0, and there is a time ti when I again come back to I for the first time, then this one is a stopping time. Okay, so now strong Markov property says that this part Markov chain is a fresh Markov chain, this one is a MC start afresh, and there is no effect of this side on this part, and so now I use this strong Markov property again. So I is recurrent, so I will come back to here for sure, that Ti is less than infinity for sure. Now starting from I, again I come back in the I, the reason being that is that Markov chain starts from here. So now if I rescale this time to 0, then basically it is basically starting from I can just forget about this part. This is basically again a new Markov chain having the same transition probability matrix. So that means that if starting from here and here the state is I will again come back to I in finite time. I am again come back to I in finite time. Okay, finite time. Next, starting from this I, again I will come back to I in finite time. So this will keep on happening. Okay, this will keep on happening, and this is exactly this statement says that starting from I will come back to I again and again infinitely many times with probability 1, and it is exactly saying that using the strong Markov property I will come back to I, again I come back to I, again I come back to I in some time, and it is just repeating again and again. Okay, now what about the reverse, that if I am given with now, suppose that this statement is hold true, suppose that now this let us call this is star. So suppose that star is true. If star is true, what does this mean? This basically mean that I will see the state I, starting from I will see the state I for infinitely many times. Now if starting from I again come back to I for sure, if this keep on happening, that means starting from I in a finite time I will come back to I at least once, because from here I come back to here, that means in finite time I have come back, and for finite time I have come back for sure. Okay, so that's why this condition holds true. That's why this implies that Pi Ti is less than infinity with probability 1, and this implies that I is recurrent. Okay, and that actually completes this proof. So this remark is important in the sense that, well, the definition tells that starting from I will come back to I in finite time for sure. For recurrent, I is recurrent. If starting from I come back to I for in finite time with probability 1, that is the recurrent state. And this remark basically tells us that basically mean that starting from I will visit the state I, the chain will visit the state I again and again for sure. Okay, with probability 1, the chain will visit the state I again and again and infinitely many times if the chain starts with state I. So starting with state I is important when we are talking about recurrent or transient state. Well, as we talk about that, we will start with I, then whether we will come back to I again and again, or whether we will come back to I in finite time for sure or not. If it is sure, then we say that it is the recurrent state. If it is not sure, we call that it is a transient state. Keep in mind that for the transient state, I may come back in finite time, but I may not be also come back in finite time. Okay, so let us proceed now. Let us now talk about what is called the passage time, kth passage time. So in the previous slide we have talked about the first passage time. So now we are going to talk about kth passage time, and then we are going to talk about what is called the excursion and the length of the excursion. So let us talk about first the kth passage time. What is kth passage time? The kth passage time is defined by this expression. So this is look quite complicated, so let us try to understand this one step by step. So first thing, that the zeroth passage time defined by default defined by 0. So Ti0 is 0 by definition. Now for k greater than equals to 0, k is greater than equals to 0, the definition is given by, it is Ti k plus 1 is defined by infimum of n such that n is strictly greater than Ti k and xn equals to I if Ti k is less than infinity and it is infinity otherwise. Okay, so let us see how what this means. So that when k equals to 0, for k equals to 0, T0 is defined to be 0. There is no problem about that. Now let us talk about k equals to 1 case. So t equals to 1. So t equals to 1, that by definition is that it is infimum of the set. Let us first talk about the first case. Infimum of the set such that n is greater than T0 and T0 is 0 in this case, and xn equals to I. Okay, because T0 is 0, that when I am talking about T1, it will come into this framework. It will come into this framework. Okay, so now basically that means that it is nothing but same as T1. Okay, it is nothing but same as what we have defined. Okay, Ti. So it is nothing but same as Ti. So this is the first passage time. If I take k equals to 0 here, actually I am taking 0. So k equals to 0 here, I get T1 Ti k plus 1. So 0 plus 1 is same as that n is strictly greater than 0 because T0 is 0, Ti0 is 0, and then xn equals to I. This is the first passage time. So T0 is by default is the 0. Then T1 is the first time when I visit the state I after the time 0, 0 is excluded, 0 is excluded here. Now look into k equals to 1, so I am now having T2I. What is T2I? By definition it is infimum of n such that n is greater than T1I and xn equals to I. If T1I is less than infinity. Okay, so that means that if this one is less than infinity, this one is finite, that means that after T1, again when I come back to this one. So I am taking the all possible values of n, after the time t1. So it starts from this point onwards, and then I am taking only those points where xn equals to I. So I am taking this point, then this point, and then if another I happens here at that point, I will take all these points, and then I take the infimum. That means this give me this point. So that means ti2 is basically nothing but after ti1, again at the time when again we come back to the state I. Okay, after the first visit to the state I, when we come back again in the state I, that is basically ti2. So ti2 is nothing but the second time I visit the state I. Okay, after time 0 excluded, second time I visit the state I, that time is denoted by ti2. Now why this infinity, otherwise infinity part is given? That is given because if t1i is infinity, that means t2i will not be visited. t1i is infinity, that means I will not visit the state I again. So t2i will not be there. t2i has to be infinity. The second time visiting is also infinity. Third time visiting is also infinity, and so on and so forth. So that's why that otherwise if it is not true, that means if tik is equals to infinity, then the next visit time has to be infinite. There is no question about that. Okay, so that means ti2 is the second time I visit. Similarly, ti3 is the third time the state I is visited. ti4 is the fourth time the state I is visited, and so on and so forth. So the kth passage time is nothing but the time, the kth visit, the time of the kth visit of the state I. Okay, time of the kth visit of the state I. Now, so let us now proceed and see that remark. The remark tells that if I is recurrent, then for all k greater than equals to 0, t starting from I will visit the state I for the kth time in finite time for sure. Okay, I will visit the kth state, ith state in for the kth time in the finite time is for sure. That is basically the statement, and the proof of the statement again using the strong Markov property, the similar argument, I mean the same argument we have given for this one, that well if I is recurrent, I will visit the state again and again. So if I visit the state again and again, that means the time to visit the ith state for the kth time is finite. Okay, I will visit the state again and again if I is recurrent, and that implies that for the kth passage time, that is which is basically nothing but the time at which we visit the state I for the kth time, that has to be finite, because I keep on visiting this state. Okay, I keep on visiting this state, so that has to be finite with probability 1 if I start from I. So okay, fine. So let us proceed, and now let us see what is called the length of the kth excursion. So the length of the kth excursion actually defined by this, it is nothing but the time difference between two consecutive visits to the state I. So in the figure it can be given in this way, that well I have visited the state I for the first time here. So S1, which is basically nothing but ti1 minus ti0, and we know that ti0 is 0, so it is basically ti1. Okay, it is basically si1 is basically ti1, which is basically the time difference here. Okay, from 0 to the first time. Okay, then ti2, which is basically nothing but ti2 minus ti1, the si2 is nothing but ti2 minus ti1, so which is nothing but the time difference here. Similarly, this one is ti3 minus ti2, and this is the time difference here. Again, this is only defined when I have this si only defined if this quantity is finite, and this one is defined if this quantity is finite in this particular manner, otherwise we see it is 0. So if this time is finite, then this time this difference we take as 0, this difference we take as 0, and if this one is finite but this one is infinite, then the length is infinite, okay. So the length of the kth excursion is nothing but the time difference between two consecutive visits, only little bit difference in the definition of SI1, which is basically TI1. The rest of the thing is the time difference between two consecutive visits, okay. So this is the kth, so we define the kth passage time, we define the length of the kth excursion. So the question is that what is excursion? Excursion is basically nothing but the path of the Markov chain between two consecutive visits of state I, okay. The excursion is basically nothing but the path of the Markov chain between two consecutive visits of a particular state, and here basically length of the kth excursion to state I, that is basically nothing but the length or time length between two consecutive visit to the state I. And of course the SI1 is defined in a little bit different way, which is TI1. For rest of them is basically the time difference between two consecutive visits, okay. Now let us talk about the distribution of this SI. Note that this SIKs are random variable because TIKs are random variables, so SIKs are also random variables. Now let us talk about the definition of this thing. So definition goes like that for distribution goes like that: for k equals to 2, 3, so on so forth, conditional on Tik minus 1 less than infinity, Sik is independent of this thing. What is this thing? I will explain. And the probability that Sik equals to n, given this one, this quantity is finite, is same as Ti equals to n starting from I, okay. So let us first try to understand this theorem using the graph. So what it says, suppose let us take, for example, let us take k equals to 2. Let us take this k equals to 2 here, okay. So if I take k equals to 2, this theorem tells that conditioning on T11 is less than infinity. Recall that T11 is same as T11 is same as T1, okay, or rather I just write the general one I, okay. So Ti1 is same as Ti. Notice, so conditioning on Ti1 is less than infinity, so this point this time is less than infinity. Sik is independent of this. What is this? This is, I am taking the collection of all m such that all xm such that m is less than equals to Ti0, okay. Xm is less than equals to Ti1. So when I take k equals to 2, I am basically talking about xm such that m is less than or equals to Ti1, okay. So it says that S2, this one is independent of all Markov chain in this part, okay. The part of the Markov chain in this part and that S2 are independent, okay. Sk is independent of the previous part. Similarly, when I talk about S3, this actually consider the Markov chain in this part when I talk about S3. So Si3 is independent of the Markov of the random variables in this part, So Markov chain in this part or the random variables in this part is independent of Si3, okay. That is the first part says, that is the independent part says. Now come to the next part. Next part tells that again if I talk about Si2, then the distribution of probability that Si2 is equals to n given Ti1 is finite is same as probability starting from I Ti1 or Ti same thing is equals to n. What does this mean? This means that, well, if I know this one is finite, then the distribution of this one is same as if I am, because here the state is I, as if now I am starting from I and for the first time I am visiting the state I, okay. Note that from here to here, when if I just if I just forget about this part, if the Markov chain actually start here from refresh using the strong Markov property. Now from here I am visit the state I here again. So from here the first time visit is here. Starting from here the first time visit to the state I is here, and this basically tells that the distribution of S2 is S2I is same as distribution of S2I is same as if I am starting from I and then I visit the state I again for the first time. Okay. So that this theorem actually quite helpful theorem to find out the distribution of Sik. It basically says that Sik is independent of the previous part of the Markov chain, Sik is independent of the previous part of the Markov chain, and not only that, the distribution of Sik conditioning on the previous time is finite is same as if I am starting from I and I am visiting the state I for the first time. Starting from I am visiting the state I for the first time. The distribution of that time is same as the distribution of Sik. Okay. So the proof actually I have the intuition I have given using this graph. Now let us write down those things clearly. So as I mentioned, the proof can be done with the help of the strong Markov property, where the stopping time can be used as the k minus 1th passage time. Okay, k minus 1th passage time. To talk about this one, I talk about this passage time as the the stopping time in the strong Markov property. Now of course in this case xt is I, because this is basically the passage time, and at this time the state is I. So provided that t is less than infinity. If t is infinite, then xt does not make any sense. Provided t is less than infinity, that this quantity makes sense, and then at that xt at the time capital T, which is same as this, the state is I. Now so conditioning on this fact that t is less than infinity, that means this time is less than infinity, which is exactly this condition. This is basically t is less than infinity because we take that t is this one. So conditioning on this part is a Markov chain with the same transition probability matrix and initial distribution delta I. That the same thing, that if I start from 0, I come at t I k minus 1, at this time the state is I. So Markov chain start afresh here using the strong Markov property, conditioning on that this quantity is finite. So that means that this is a Markov chain, in this part is a Markov chain which is again having the same transition probability matrix, but the initial distribution is delta I, it is starting from I, and this part is independent of this part. These two parts are independent. These two parts are independent. This is the strong Markov property tells us. Okay. So now look into the definition of this. The definition of this was that Sk was basically the time difference. If this time is T I k minus 1, if this time is T I k, then this is the time difference. This time difference is basically Sik. Now if I look into the next part, this part, if I start from here on this side, then this time difference can be written as after this point when I again visit the state I. So this is nothing but n is greater than equals to 1, such that x t plus n equals to, I takes the collection of all such n and I take the infimum. After this, when I see the state, this state. So this is basically this one. Okay. Notice that this t is same as this quantity. So this is basically my t here. So t plus n is basically means that after this time when again I see this state I. Okay. So that means this is basically after this, what is the first passage time? After this, what is the first passage time? So Sk is the first passage time of this Markov chain. Sk is the first passage time of this Markov chain, and the strong Markov property says that this Markov chain is this is a Markov chain having the same transition probability matrix starting from I, and this Markov chain now is independent of x0 to xt, which is basically this part of the original Markov chain. So this shows that, well, this first quantity hold true because Sk is the function of this part of the Markov chain, Xk is the function of this part of the Markov chain only, Sk is the function of this part of the Markov chain only, and the previous part, this part is basically this quantity. So clearly Sk has to be independent of the previous part, and then basically the next part is basically given by the fact that, well, once I come here, everything start afresh. So from here it is basically again when I first time I visit this one, so from state I, this is basically nothing but when I again visit the state I. Okay, so this is basically the proof. So the takeaway from today's lecture is that we have defined what is called passage time, and using the first passage time we have defined what is called the recurrent state and transient state. Recurrent state basically mean that starting from the state I will come back to the state I in finite time for sure, and transient state mean that starting from I there is a positive probability that I will not come back to I in a finite time. Now the intuition of the recurrent state is that starting from I will come back to the state I again and again for sure, and then we talk about the distribution of the kth passage time, and we pointed out the fact that the kth passage time is independent of the previous part of the Markov chain. Kth passage time is independent of the previous part of the Markov chain, and the conditioning on the fact that the Ti k minus 1 is finite, the distribution of the kth passage time is same as distribution of the first passage time starting from I. Okay, distribution of the first passage time, conditioning on that the Markov chain is starting from the state I. With that I stop in the lecture. Thank you for listening.